differentially private programs, not these other differentially private programs. Thank you.
Howdy, y'all. Right, I'm going to talk about differential privacy again. A very high-level view, differential privacy is a mechanism by which we can allow data analysts to access data by basically evaluating a query and then adding some noise to the result. In practice, if an analyst is submitting a query to some database that's being protected by differential privacy, they're going to get back just a single value that's been sampled from this distribution that's constructed. For the context of this talk, though, we're going to peel it back just a layer and think about differential privacy as a mechanism by which we can take a query and produce a probabilistic program, as in just one that produces a probability distribution as its output. Now, I don't know if y'all have heard the news, but a lot of people like differential privacy, including Apple, Google, and the US Census Bureau. So there's definitely some interest, and there's definitely a lot of people that would like to use differential privacy, but there are some issues with this. Namely, differential privacy is difficult to get right, even for experts. This is a screenshot from a VLDB 2017 paper that includes 6 different implementations of the SVT algorithm. They all have their own privacy claims and their own implementations. You can see syntactically they're all pretty similar, but only 2 of them actually satisfy the privacy claims. So this is problematic. In fact, some of these algorithms that are correct and some that are incorrect were done by the same person. So even people who know what they're doing still have a chance of getting these things wrong. And to me, this indicates that we need to be able to, we need to do better for everybody else. So our goal for this work was to enable access to sensitive data by synthesizing privacy-preserving functions from very simple specifications. The functions that we really care about synthesizing sort of take 2 flavors. The first flavor is we'd like to synthesize queries, where some sort of domain expert, not necessarily in differential privacy, wants to access some sensitive information. For example, maybe somebody is concerned about comorbidity rates or cancer occurrences or things along those lines. We are also interested in helping the people who are designing these privacy algorithms, and so we really care about synthesizing whole-scale differential privacy algorithms. Don't worry, this won't be on the homework. It's a fairly complicated algorithm. I just want to give you a taste of what our synthesis procedure can do. We can fully synthesize this. This is taken from a 2013 paper that introduces the system DFuzz, which I'm going to talk about in just a few minutes. So I'm going to give a slightly different perspective of privacy. As robustness. As we've seen in Hengchu's talk, really what privacy is if we're given 2 similar inputs and we want to apply some query, we should expect 2 similar outputs. So if we're given 2 medical databases and we want to know how many people have had some form of elective surgery or something along those lines, if those databases are very, very similar, say there's only a few people that are changed in there, we would expect these output distributions to be very similar. We're going to quantify this similarity using metrics. Okay, so we have a metric on databases and we have a metric on output distributions. And so really the privacy guarantee is that if we start with 2 databases that are very close together, then the output database or the output distributions that we're going to get are only going to be at most epsilon apart, where epsilon is this tunable privacy parameter. The smaller it is, the closer these distributions are together. The larger it is, the further apart they can effectively be. So to get our hands on programs that satisfy privacy constraints, we're going to use a system called DFuzz. DFuzz was one of the papers mentioned as sort of the spiritual successor to Fuzzy. And this is a DFuzz type. It looks complicated, but we're going to break it down. Effectively, this is the Laplace mechanism. It's what we saw on the previous slides. It takes in some query and it adds some Laplace sampled noise. So the first argument to this function is the privacy parameter. This sort of tells us how far apart we want the output distributions to be. The second input to the Laplace mechanism is some query that you want to evaluate, right? It takes in some database and it produces some real value number. Now the third input is the actual database we want to evaluate this on, and the final term in this type is the return result, which in this case is a distribution over real numbers. And just looking at the syntax of this type, we can already determine some of the features that DFuzz has that we can take advantage of. First off, it has a probability monad, so we can actually reason about distributions at the type level. That's quite convenient. Second off, it actually has dependent types. So we can do things like take in privacy parameters and use this to reason about the sensitivity of these functions at the type level. And the last important feature is these linear sensitivity annotations. Anytime we see this function application, this linear implication, we annotate it with an index that basically says how much the output can change given a small change in the input. This is all done with respect to the metrics that we have on every single type. So for every type in the system, there exists a metric. If you have lists, you need to understand the metric for the type of lists, for example. And effectively, this is a form of continuity or robustness. Now, this is a lot of setup, but the payoff is quite something. Defuzz comes along with this very nice metric preservation theorem, which effectively for free gives us the fact that any function that has this particular type, it maps a sigma and is epsilon, it maps a sigma to distributions over taus and is epsilon sensitive, is necessarily differentially private. Now, considering our robustness interpretation of differential privacy, perhaps this is no surprise, but it really gives us a tool by which we can get our hands on synthesizing differentially private programs. Namely, all we have to do is perform type-directed synthesis starting with this type. Now, if you're not familiar, type-directed synthesis is sort of an effective inversion of type inference. Instead of asking something like, here's a context in an expression, I want to know what type it is, I'm really going to be asking, here's a context and a type, give me as many expressions as you can that make that typing judgment valid when plugged into the exclamation point, or the question mark. If we can solve this problem, we're going to be able to synthesize differentially private programs. So how do we actually solve this problem? Well, the first thing we need to do is we need to extend our term language with what we call wildcards. Wildcards have a few annotations. In the superscript, you can see a typing context, and in the subscript, you can see a type. And really, you can think of these wildcards as a possible solution to the type directed synthesis problem that we posed in the previous slide. So any expression or any wildcard can be replaced by an expression E, and the resulting type inference judgment will be valid. So what we're going to do is we're going to search over the space of all possible terms by starting with a wildcard and iteratively refining it to make it more and more grounded. And we're going to do so by inversion of the typing rules. Really what this refinement looks like is pretty simple. We just need to know what the goal type is and what the starting context is. So for example, if our context is empty and we want something like a natural number, we can refine this wildcard just to be 1 or 2 or 3 or any natural number you might pick. If our context contains a variable that is of type tau and we want something of type tau, of course we can just refine the wildcard to be x. Perhaps more interestingly, if we actually want a function, if we want to map a sigma to a tau and we have some context gamma, we can introduce a lambda abstraction. This actually introduces a new wildcard into the body of the expression. The type is now different. Instead of looking for a sigma to tau, we're just looking for a tau. And we're able to extend the context with the knowledge that x actually has type sigma inside this expression. Okay, well, to invert typing rules, we should probably take a look at one of Defuzz's typing rules. This is the typing rule for function application. It looks pretty similar to any other function application you might have seen, except for some slight technicalities in how we're going to be combining the typing contexts. Right. So if we have an f that maps taus to sigmas and we have an e of type tau, certainly we can apply f to e and get something of type sigma. But the problem is f is case sensitive, and e contains some uses of variables. So as we apply f to e, those uses of the variables are sort of going to be magnified by the sensitivity of k. So really, in the consequent, we really need to be taking this linear combination of typing contexts. And the reason is because these defuzz contexts maintain the sensitivity of variables inside their variable associations. So instead of just mapping x to sigma, we're going to be mapping x to sigma with sensitivity k. So if that variable association is actually used in a valid typing judgment, really it says that the expression that's being typed must be k-sensitive in x. Because of this, this context arithmetic effectively just takes all the variables and combines their sensitivities linearly. Now, we want to be developing some inference rules for our refinement judgment. The kind of inference rule you might expect if we're doing something like inverting function application might look a little something like this. If we're looking for a sigma, certainly we can get a sigma if we find any expression of type tau to sigma, and then something of type tau, and just apply the two together. The problem is this isn't quite an inversion of this typing rule because this only holds if gamma is equivalent to gamma 1 plus k times gamma 2, if we can actually do this linear decomposition of gamma into gamma 1 and gamma 2. And the problem is, in general, there's going to be infinitely many ways of actually decomposing this gamma. So when you're doing synthesis, at some point in time, you're going to have to make a choice, and we really don't want to do that. So one of the key ideas that actually makes this work is the fact that we're going to be using symbolic context to express our decomposition. So what this does effectively is transform our inference rules for this refinement judgment over wildcards to look a little bit something like this. Instead of just keeping track of expressions, we're also going to be keeping track of a constraint system. And now the wildcards, instead of maintaining type and context, are going to be maintaining type context variables. So what we can do inside our constraint system is accumulate the constraint that the type context for the original wildcard is equal to the appropriate linear decomposition of the type context in the consequent. A couple of key things I want to point out here is that effectively what this constraint system does is tells us when this expression is well typed. This is quite convenient. It's also being monotonically generated. We're only ever conjoining on new constraints. It's never really going to get simpler as we're doing our synthesis. And this is going to be helpful for the next slide. Okay, so now let's assume we have our set of inference rules that define this refinement relation. What do we do with that? Well, we're still looking for a solution to this type-directed synthesis problem. We're looking for a differentially private program. So what we can do is we can generate the synthesis state that looks a little bit something like this. It's basically just saying we're looking for an expression of type sigma to delta tau that's epsilon sensitive inside context gamma. So we can, in theory, non-deterministically, but in practice heuristically, apply all these different refinement rules, and we end up with a search tree. And we're looking for some ground term that has a constraint system that is satisfiable. Now, conveniently, because our constraints are being generated monotonically, if we ever arrive at a situation where, for example, phi sub 1 is unsatisfiable, we can go ahead and just prune the entirety of the subtree. As the constraints are being generated monotonically, there's no way we're ever going to come up with a valid solution. This might happen, for example, if we take a synthesis step that guarantees that no program is ever going to be able to satisfy privacy. For example, maybe we just go ahead and release the entirety of the database. That would be bad. Of course, these constraints are over typing contexts, which is not a common theory that you're going to find in most SMT solvers. So to check satisfiability, we have to convert it to an equisatisfiable formula in the theory of nonlinear real and integer arithmetic extended with infinities, which is problematic because in general that's undecidable, although it turns out in practice that the kinds of constraints that we're generating are fairly simple polynomial equalities and inequalities, and so in practice it's often decidable. But there's another problem, unfortunately, in that if you actually want to be checking satisfiability of these constraint systems every single time you take a step in the synthesis, the overhead of actually calling out to an external SMT solver is going to massively outweigh the benefits you get from the reduction in state space. So instead, in practice, what we have to do is take this constraint system, simplify it a little bit, and sort of heuristically direct the search away from solutions that are likely to be unsatisfiable. Basically, the more constrained one of these constraints is, the further away we want to stay from it. So now that we have a mechanism for taking these inference rules and converting it into a search procedure, we built an implementation around it. So we have a synthesizer that is effectively a fair scheduling of these inference rules. It takes in as input a set of input-output examples that characterizes the semantics that a person would desire for one of these queries or one of these algorithms, as well as a privacy budget. You can think of this budget as really just a constraint on your privacy parameter epsilon. The synthesizer also takes in a set of mechanisms and components. These can be a variety of things, from projections from rows of a database to something like an age or an eye color or something along those lines, to things like sums, folds, filters, maps, averages, all the way up to whole-scale privacy mechanisms like the Laplace mechanism itself, as we saw at the beginning of this presentation. Now, one nice thing is our synthesizer, because it does a fair scheduling, is sound and relatively complete. We do place some slight syntactic restrictions, so we can't generate everything, but if it lies within our syntactic restriction of defuzz, we will eventually find it. And we're able to produce arbitrary defuzz programs within the syntactic restriction, which is important because defuzz has a lot of features that I haven't had time to talk about here. For example, it has sensitivity polymorphism. It has recursion, which we handle a fairly limited form of. It has dependent pattern matching. And these two things combine to allow you to do some really complicated algorithms that are guaranteed to be differentially private by construction. It also has subtyping. Sometimes we can use a less sensitive function in place of a more sensitive function. We need to be able to reason about this during synthesis. This necessitates an abduction judgment that we have to include as well for refining our constraints. And there's a lot more here. If you're interested in these details, I recommend you check out the paper. Now, for benchmarking, remember, we're interested in enabling not necessarily privacy experts to access this kind of information. So we gathered a few publicly available real-world data sets that have information that we consider sensitive and possibly important. Things like recidivism scores, school performances, alcohol consumption, home life, the kind of thing that you don't want just anybody looking at, but can have some fairly serious like socioeconomic implications in some situations. So the kinds of solutions that we're looking for are something like this example up here. This is one of our benchmarks from the recidivism score benchmarks. It's looking for the average failure to appear score, which is something that's computed by the COMPAS mechanism for young people with no priors. Now, we know we can synthesize these things, but is it worth all the overhead of actually keeping track of all these sensitivities and using something of a complicated type system to do synthesis when just pure enumeration might be better? Well, it turns out, yes, you can get some pretty good benefits. So here I've taken each one of our benchmarks and I've plotted it as a dot on this graph. The x-axis is the time it took to synthesize this solution to this particular benchmark using our sensitivity-directed mechanism. And the y-axis is the time it took for a regular type-directed benchmark that we implemented. This is a log-log scale. So each of these 3 lines that you see are efficiency curves. They're pretty close together, but the top and the bottom are 10x and 0.1x efficiency respectively. And as you can see, nearly every single one of the benchmarks lies in between the 1x and the 10x level curves. Some of them go over the 10x. That's pretty good. And very, very few go under. On average, if you take all these, we end up with about a 4 times improvement over the type-directed baseline with respect to the time it takes to synthesize a solution. Now, I did mention at the beginning that we're also able to synthesize algorithms, as in the iterative database construction algorithm or something like k-means. If you're interested in that, we have all those details in the paper. So to conclude, I've presented a mechanism by which we can use defuzz to automatically synthesize differentially private programs from simple input-output examples. This has the ability to really open up this sensitive information to all kinds of people to help sort of democratize data access and to make sure that people can actually get privacy right. If you're able to synthesize small snippets of differentially private programs, that can be really convenient, and it really opens up the door for a lot of interesting future work when you want to combine it with various other kinds of analyses. For example, if you're concerned about things like side channel attacks, maybe you want to do the synthesis also with respect to other resources such as time or memory consumption or something along those lines. Or if you're able to automatically reason about the accuracy or the utility of these differentially private queries, now you might be able to do something like query optimization, where I can synthesize possible solutions and evaluate them and compare and see which one I actually want to keep as a solution. That's all I have today. Thank you for your time, and I'd love to take any questions.
So first, a quick question from Slido. Where is your work, and is it available?
It is not available yet. It will be soon.
OK.
If you're interested, come talk to me, and I can hook you up.
Question from the audience?
Hi. This is really fantastic stuff. So I was interested in that you also had the input-output examples going into the synthesis engine.
Right.
So could you just say a little bit about how that sort of squares with the type-directed synthesis?
Sure. So there are definitely some type-directed works that also consider input-output examples sort of at the type level as they do their synthesis, and they use these input-output examples to direct the search. We don't do that. And one of the reasons we don't do that is because we want to be able to handle a wide variety of applications and benchmarks, which really means that one of the inputs to our synthesizer is a set of arbitrary components. So to be able to propagate these input-output examples in a meaningful way to prune the search would require us to reason about these arbitrary black box functions. And since we don't do that, really we just use these as a check at the end to make sure that we've got the intuition right.
OK, thanks. Yeah, makes sense.
Another question from Slido. So can you talk a little bit about your heuristics you use and how you can avoid things like trivially private programs when you're synthesizing?
Sure. So one reason we're able to avoid something like a trivially private program is, again, because we can place things like this privacy budget. If you want to have something like a trivially private program, I could just enforce epsilon to be 0, and that means that every output has to be the exact same distribution. That's not particularly useful. So instead what you can do is you can actually place bounds on this epsilon to say it's greater than some value and less than some other value. Sometimes this is an economic procedure, sometimes it's not. And this really allows you to make sure that the thing that you're getting is not overly private. As for the heuristic, we take this set of constraints and we simplify them as much as we can using something like unit propagation, and then we are able to take a look at how many variables are constrained, how they're related, what are the coefficients and the polynomials, how many infinities are floating around in there, things like that. And we're able to come up with a fairly reasonable guess as to sort of how unsatisfiable the system might be in like a model counting sense. Not really a model counting sense because the models are real numbers. But then we use that to direct away from these constraints that are likely to be unsatisfiable.
From the audience, anything? Yes.
Thank you. That was cool. Thank you very much. Do you get any, so by virtue typing, you get that your programs that you're synthesizing are differentially private, do you get any guarantees about functional correctness?
The only guarantees about functional correctness we get are up to the specification that the user provides.
Okay.
And functional correctness is a little bit weird to think about when you're considering differentially private programs because they're necessarily probabilistic. And so if you have some sort of deterministic semantics that you want to encode, things can get a little bit tricky when I'm returning random results. But really, our system is able to take in pretty much any kind of specification that you would care about in terms of input-output examples, or just an actual strict like functional specification of what you want the output to be. And once we synthesize the solution, we check against this constraint, make sure it actually matches. So if you care about functional correctness, we can get that, yes.
So the input spec is both, can be both input-output and functional spec?
Yes, and there are some cases for some of the benchmarks where we might take input-output examples and then convert them into some sort of functional specification when the semantics of what the person is specifying don't necessarily match with the semantics of what we're trying to synthesize due to the way that noise is added.
Thank you.
Great. Well, let's give the speaker another round of applause. And,